Good morning, sir. Myself Lakshmi. I am from ECE department. Today I am going to explain about parabola reflectors. These are the contents I am going to explain. Introduction, types of parabolic reflectors, advantages, disadvantages, applications and conclusion. Introduction to parabolic reflectors. Parabolic reflectors are specialized structures shaped in the form of paraboloid, designed to focus energy such as light, sound, or radio waves to a signal point known as the focus. The fundamental property of parabola reflectors that any incoming rays parallel to the axis of the reflector are reflected to the focal point, enabling efficient concentration or transmission of energy. This unique characteristics makes parabolic reflectors essential in applications that require high precision in directing or gathering waves or signals. The concept and use of parabolic reflectors back to classical antiquity. The mathematical diagrams first describes their discussing property in the context of burning mirrors. Are is said to have studied paraboloids of hydrostatic context, and although legends claim be used that reflectors to set energy ships on fire, historical evidence is lacking. In the 13th century, Ruser Bacon further studied parabolic mirrors, and in the 17th century, James proposed parabolic mirrors for telescopic to eliminate spherical. Parabolic reflectors are approximately is lighthouse technology before being replaced by Fresnel lasers in the 19th century. Designed to reflect waves originating from directed towards its focus. When waves from a distant source strike in surface, they are reflected and focused at a specific point called focus, enabling the collection of concentration of energy. Conversely, when the source is placed the focus, the reflector efficiently creates a directed parallel beam of radiation. These are the key properties of parabolic reflectors, that is reflection and high directivity. And types of parabolic, these are the types of parabolic reflectors. Paraboloid dish reflector, cylindrical parabolic reflector, shaped beam antenna, prime focus, axial or focal bead. Uh, Next, derivation of parabolic reflectors. These are the two cases we take to derive the parabolic reflector gain. First of all, the power P equals to from the figure A, P equals to dy into Sy. Sy is the pointing vector, and P equal and another power representation is P equals to d theta and u dash. U dash is the power per unit angle per unit length in the direction. Sy Compare compare the above two equations. Power equation Sy dy equals to u dash d theta. Sy by u dash equals to 1 by d by d theta of y. From the above, r equals to 2l by 1 plus cos theta. Substitute that r value in the above equation. Sy equals to 1 plus cos theta by 2l into u dash. We take theta equals to 0, then 1 plus cos theta by 2l into u dash. In the place of theta, we replace 0. Cos 0 equals to 1. 1 plus 1 by 2l into u dash, that equals to s naught equals to u dash by l. We want to find the electric gain power of the parabolic antenna. So e theta by e naught equals to the square root of 1 plus cos theta by 2. From the second figure, we take rho equals to r sin 2 pi r sin theta, and the another power equation equals to 2 pi rho sin theta. Compare the above two power equations. We get 2 pi get cancelled, and rho sin theta equals to sin theta and d theta. From that, s rho equals to 1 plus cos theta whole square by 4l square into u. The ratio of the power density s theta at the angle of theta at the power density s naught at theta equals to 0 is s theta by s naught equals to 1 plus cos theta whole square by 4. The field intensity ratio in the aperture plane is equals to the square root of the power ratio e theta by e naught equals to 1 plus cos theta by 2. These are the parabolic reflector feeds. First one is rarefied using half-wave dipole, and the second one is rarefied using horn, front feed using horn, and offset feed using horn. And high gain and directivity. Parabolic reflectors provide very high gain and simply focused beams, which make them ideal for longer distances, point-to-point communication, and precise signal targeting, and reciprocity, and efficient aperture use, and minimal power waste. Disadvantages of parabolic reflectors are radiation blockage, complex design and alignment, size and weight, and narrow bandwidth. Applications of parabolic reflectors are mainly used in satellite communication, radio astronomy, microwave and wireless communication, radar systems, and parabolic microphones and lighting. Conclusion. Parabolic reflectors deliver very high gain and directivity, making them essential for long distances and point-to-point communication links. Their reciprocal operations allows use for both transmitting and receiving signals with equal accuracy. And feed and support structures are cause signal blockage, reducing the overall efficiency, especially for provide focus designs. Thank you.